So now let's go around the world and think about plate tectonic settings. And generally, what you need to look for is an orogeny. An orogeny is the kind of thing that happens with a continent-continent collision, or perhaps a continent-microcontinent collision, or even a continent-island arc collision. So we're going down the scale from the largest continents to continents colliding with much smaller features. Now, the biggest active orogeny in the world today lies at the junction between India and Asia. We have the India-Asia collision, which began about 50 million years ago and is still ongoing, with India pushing up against Asia, the result of which is a large deformed area and a hugely thickened crust under Tibet. It's as much as 70 kilometers thick, which puts you well beyond normal high-pressure metamorphism, well into the ultra-high pressure metamorphic zone at the base of this crust. So if you were to come back tens of million years from now, perhaps you would find very high-grade metamorphic rocks in the location that is now Tibet. But today it is still actively being produced. An area that shows evidence of multiple periods of metamorphic processes is the Alps. And in this photo, you can see that there is an interaction between the African plate, the Arabian plate, and Eurasian plate. They have been juggling against each other for hundreds of millions of years. And in the juggling zone between them, they have pushed together and shoved the rock down into metamorphic regimes of pressure and temperature. Here is a current illustration of the Alps. You have Italy, the flatlands to the right, the Alps, and Germany, the flatlands to the north, or the left side of this image. In between, you have this crumpled zone from the most recent shoving of Africa towards Europe. It has shoved up rocks that were metamorphosed in yet earlier episodes of jiggling between Africa and Asia. Now, there's an even larger collision zone that occurred about 400 million years ago, and that's when North America, Africa, and Europe all came together to form the supercontinent Laurasia. Well, Laurasia is actually the northern supercontinent. There was a Gondwana land in the south, or Pangaea, when you consider all of the continents together. Now, when North America and Europe came together, it closed what had been an ocean between them. This is called the Ancestral Atlantic Ocean. Here's a map that illustrates the arrangement of the continents some 400 million years ago. You have North America pressed against Africa. You have Greenland caught between North America and Finno-Scandinavia, with Europe lying to the south of that. There's the suture zone in yellow. That's where the plates came together, the continents came together 400 million years ago. Now you'll notice this suture zone is not where the plates pulled apart to form the modern Atlantic Ocean. You'll notice that prior to the collision, the northern part of Great Britain was attached to the North American plate, whereas now it's attached to the European plate. Anyway, during the collision, we had something much like the India-Asia collision. We had crumpled zone between the continents and intense metamorphism going along the suture line. And here in North America, you have the remnants of that metamorphism showing up in the Appalachian Mountains, running all along the east coast of the US and up through New England. In England, again, you have intense metamorphism dating from the same time. And along the western coast of Norway, the fjordlands also show this intense metamorphism caused by the collision of the plates to form Laurasia. Let's turn now to the western United States. And here's a map showing most of the western United States from Alaska down through Mexico. And one of the things you notice is the shading of colors along the western side. and that goes deeply into the continent, back almost to the Rocky Mountains. All of this zone from Montana to the coast in Washington is what is called accreted terrains. They are microcontinents, island arcs, and such that have been scraped off against North America. Let's look in particular at the regional setting for metamorphism in Washington State. And I'll do this with a cartoon showing you a sequence of events from North America on the far left to microcontinents sitting off the coastline. These microcontinents may not be granitic, they may be mostly basaltic. They came in attached to the oceanic plate. In between the accreting terrain and North America, you had a basin that could have filled with very thick sediments as they approached each other. As the microcontinent docked against North America, the sediments trapped in between were crumpled, distorted, and faulted, and pushing together would involve reverse faults, pushing lower layers over the underlying layer, or upper layers over underlying layers. With the docking, the subduction zone moves out to the outboard side of our docked terrain. And this crumpled zone is now pushing the formerly surface rocks down to depths at which they can be metamorphosed in regional metamorphism, as shown there with the orange circle. Now in our case, we also had additional microcontinents coming in on the plate. And again, you could have another zone of sedimentary basin between the plates as the continental fragments were coming in. And as the new terrain docked, in fact, it crumpled further the regime of the old docked area. And you see now we've moved the subduction zone still out farther. Let me back that up again and show you how regionally metamorphosed rock between the first microcontinent and North America is shoved up and over underlying rocks to reach the surface. It is this kind of tectonics acting on earlier metamorphosed rocks that has brought materials to the surface in the North Cascades, and it's this kind of rock that now makes up Mount Shuksan in the North Cascades. So let's look at a local map of the Washington State, and I'll point out you have Seattle to the south, you have Bellingham farther north, you have the Canadian border running across as shown by the black line. Running down the Cascades is a separation in the North Cascades between a green schist zone to the west and an amphibolite zone to the farther east. Mount Shuksan sits right in this green schist zone near the Canadian border. And here we are again where we started with metamorphism, with a view of Mount Shuksan, which I told you at the beginning was green schist. And now we have an idea of what green schist means. It's a metamorphic facies acting at modest pressure and temperature in metamorphic environments. In the case of Mount Shuksan, we have a large thrust fault running from the south towards the north, pushing Mount Shuksan over a lower layer of phyllite. The phyllite was oceanic sediment that has been only moderately metamorphosed, and above the fault is green schist facies metabasalt. Meta for metamorphic, basalt because it was the crystalline oceanic crust at one point in its history. The fault motion has pushed the Mount Shuksan massive from the south towards the north, and that thrusting occurred during additional docking of material against North America.